ठीक है. So octahedral complexes के case में, what does CFT talk about? Like how does it explain the magnetic structures and color and all of that? Okay. So like when the metal atom is on its own initially, okay, so there's no ligands around it, it's happily there chilling around. We do that. So if this is the energy diagram, it has like all the orbitals have certain energy, certain amount of energy. Right? This is when the metal atom simply exists. So this is what you had studied in atomic structure, right? Like every shell orbital has a certain energy associated with it. That's the default. Okay, next.
Is this like a graph?
Yeah. Here I'll be drawing the graph, and Nietzsche I'll also be drawing like what is happening in that scenario.
So what are E is for energy?
Yeah.
Then what are those lines?
Oh, I've drawn
Metal.
5 lines for the 5 d orbitals.
In the metal atom.
Yes. Okay. So since they all are of equal energy, they're said to be degenerate. Degenerate orbitals matlab like all the orbitals have equal amount of energy, the 5 of them. Okay. Then you have the metal atom, but now it is surrounded by an like negative charge, but all around it, like in a spherical way. So whichever direction you go in, like the negative charge is equal. So what can you say about the energy of the orbitals here as the negative charges are approaching it?
It will increase.
Yes. So like electronic orbitals are already negatively charged. Negative charges are approaching it. So because of the repulsive forces, you're going to have that potential that is created there. So in this scenario, again, because it's equal in all the directions, the 5 orbitals will still have equal energy, but they will have increased amount of energy.
So it's degenerate even here.
Yes. Okay. So this is
But like degenerate as in?
Degenerate simply means with equal energy. Degenerate orbitals means all these orbitals have equal energy. So no field. So here we have a spherical field. So increased energy, but still all are equal. Now we come to our special case, but this is not what happens in reality. In reality, we have our metal atom being approached in an octahedral structure. There's only 6 ligands, and they are approaching the metal atom in an octahedral shape. So you have a negative charge here, top, bottom, this way. Yeah.
I might not understand the degenerate part. What is that?
No, degenerate means equal energy.
So the energy is increasing, but all 5 will still remain equal. Like that.
Yes. Yeah.
And
Okay.
how was it increasing?
Because you have a negative charge surrounding it due to the repulsive forces between the orbitals and the electric field here. Uh, you have increased energy. Okay. Now, instead of spherical being equal all around, you have ligands which are negative charges approaching only in certain places, certain spaces here. What do you think will happen?
And because of the presence of negative charge, how is the energy increasing?
Repulsive forces hai na. So whenever you have like electronic interactions, so there's a potential being created. You have to like spend energy to push it against each other, right? If you have to like do work for that, conservation of energy, so there is potential energy existing which you're working against. So this is like, take it by default, if you have charges interacting, there'll be energy. Like this is something we've seen right from structure of atom, like between the nucleus and the electron there's like energy present. Even chemical bonding may, when two atoms are approaching, you have that energy like the potential energy diagram that happens. So whenever charges interact, you have like some sort of energy that's present, potential energy, electric potential energy basically. Okay. Okay, so when this is being like, when the negative charge is approaching specifically only in octahedral directions, will the orbitals still all have equal energy? Like, will they have equal amount of repulsions?
No.
So the reason lies in the shape of the d orbitals. Do you guys remember which the 5 d orbitals are? What are the different types of d orbitals? 5 of them.
dxy, dyz, dxz, and dx square y square something.
Yeah. The 5 of them, you have dxy, dyz, dxz, and you have dx square, y square, you have dz square. So dxy, if you look at the shape, it is in between the x-axis and y-axis, right? So if we say, let's say, do you guys, can you imagine 3D geometry? You have 3D, 3-axis, x-axis, y-axis, and z-axis. So imagine that, like, let's say this was x-axis, this is y-axis, and upper niche is z-axis. Will, like, what is the effect of these negative charges on dxy orbital? Will it be more or will it be less? xy?
More,
Why?
because like it lies at the xy plane and there are like 4 points where it's attacking.
No, but it's in attacking from here, like from here, no? The orbitals are oriented from here. So if you compare it to dx square y square, which is located directly on the axis itself, the ones in between the axis will face less repulsions. The orbitals that are on the axis will face more repulsions, right? So now all 5 orbitals will not be of equal energy. The orbitals that face more repulsions will have higher energy, and the orbitals that face less repulsions will have lower energy. Okay, so which means the d orbitals are not degenerate anymore. They split. So this kind of splitting is called crystal field splitting. So let's see, octahedral mein along the axis will have higher energy. So you have d x square y square and dz square. And lower isme you have three of them, the ones that are in between the axis. Dx, like here. So we'll talk about crystal field splitting later. I'll give you the proper definition. Okay, this will be dxy, dyz, and dxz. So this split occurs. So just summarizing the whole thing. This is the default energy, like metal is independent free, default state where it's at. If you have an electric field approaching it, like a negative electric field approaching it, spherically equal in all directions, then energy increases due to repulsive forces, but still all of them are still at equal energy level. But that's not actually what happens in reality. In reality, what happens is you have like coordination number 6 hai, if you have only 6 ligands that are bonded to the metal atom, they will approach the metal atom in octahedral shape, octahedral directions, which means all the orbitals are not equally affected. It's not spherical in nature. It's affected only at certain points. So based on that, the ones that are directly affected by the negative field on the axial points, x-axis, y-axis, z-axis, these will have greater energy. And the ones where it's not directly approaching, which are between the axis, these will have lesser energy.
We have to remember this graph.
Yeah, you remember this explanation. The main thing you need to remember is that octahedral complex may dx square dy dz square will have higher energy, dxy yz xz will have lower energy. So the ones that I'm highlighting in like red, that's the most important part that you need to know. So there's more related to it. So once you guys are done noting this down, I will write it in a fresh sheet so that it's not all like straight up.
What is that no field that you have written? Sorry.
One second, sorry. I'm just want to let you know that the meet is gonna get shut soon, so note down quickly.
Ma'am, what is the no field that you've written?
Oh, so 3 cases, right? No field, lowest energy, all equal default state. And spherical field is what if when it's surrounded quickly, this is the case. Octahedral,